So we're good.
Okay. Hi, everyone. You are welcome to the fourth day of the summer school. And today we'll be discussing cosmology. Two lecturers will be taking the course. Professor F.C. Odo of the University of Nigeria, Nsukka, Department of Physics and Astronomy, and Professor Amaria Bebe from the Northwest University in South Africa. The first lecture will be taken by Professor Odo. Prof, over to you.
Okay. Thank you for introducing me. Let me share the slides. Good. Can you see my slide now?
But it's not in presentation mode.
Okay.
Okay, that's fine now.
Good. This one. Okay. Yeah. Good morning, everyone.
Good morning. If you're talking, we can't hear you. Okay, go ahead.
Good. So as an introduction, the best way to start this course is by defining what cosmology is. And cosmology is a branch of astrophysics that studies the origin, the evolution or history, and the ultimate fate of the universe in which we live. So the study of cosmology is already an old science because since the beginning of civilization, humans have always asked where they came from. And in cosmology, some of these questions like where did we come from and where are we going may be answered. So this cosmology is a science that uses the entire universe as its laboratory. So we look at the galaxies, however big they are. In this case, they are looked at ordinary point particles. So when we look at cosmology, we begin to understand it from the human perspective. It's just like somebody that suddenly emerges at the center of a very long road. He didn't know where he came from, and he's not aware of where he's going. And from that center of the road, he's thinking of how to understand where the road started and where the road is ending. So you can see that cosmology actually is a very difficult aspect of astrophysics. And in that case, it will have to do with a lot of abstract imagination. So if you look at the universe as we know it, if you look at our address in the universe, the Earth is inside the solar system, and the solar system we have been taught in the first lecture in this series that the solar system is inside one of the galaxies called the Milky Way. So, and these galaxies are now the basic contents of the universe. So in cosmology, when we are looking at objects, when we talk about objects in cosmology, we are looking at these galaxies. You can see that the objects of interest in cosmology are actually very big objects. Because the Earth, as you know, as a person, you will see the Earth as a very big object. But when we look at cosmology, the Earth is very, very small, too small to be considered as an object. So in cosmology, what we look at as an object is a galaxy as large as it is. So as I said, looking at it from the perspective of somebody that emerges at the center of a road, not knowing where he came from and not knowing where he's going. The best way to start looking at it is to look at your surroundings. And as much as we can see, when you look at the universe, it presents a picture that appears in the form of what you see on the screen. And looking at that, one thing we can glean out of it is that the whole thing appears to be uniformly distributed. The dots appear to be uniformly distributed all over that surface. So based on that, there is a cosmological principle, which is actually the cornerstone of modern cosmology. So this cosmological principle sees the universe as a homogeneous and isotropic system. What do I mean by this? Homogeneous in the sense that the distribution of matter is uniform all over the universe, and the universe looks the same in every direction. So homogeneity in this case means that the density distribution of matter is the same at all points. So what you see at one point is also what you see at another point. If you face any direction in the universe, they all look alike. So that is the concept of homogeneity and isotropy, which is the basic principle upon which modern cosmology is hinged on. So if, for instance, from this my analogy, if this man at the center of the road wants to look at and understand where he started, what he will do is that he will think of looking for the most distant objects along that path. So that is why in cosmology, we try to look at the most distant objects. Because when we look at these most distant objects, we are trying to look back to understand where we are coming from. So because of this, in cosmology, some very distant objects that are known are the radio galaxies and the quasars. These galaxies and quasars that are observed in the radio band. Radio band because the radio waves have traveled over very, very long distances before reaching the point of observation on Earth. So by implication, these radio galaxies and quasars appears to be most important objects used in cosmological studies, which can give us information about the history and evolution of the universe. So the cosmological principle has a lot of implications. Implications in the sense that there are certain observations, certain effects that come out of that, which need to be explained. So for instance, if the universe is homogeneous and isotropic, which means at any point you stand or at any point you observe the universe, what you observe there is very likely looking like what you can observe from any other point in the universe. So the implication of this is that the universe has no center and the universe has no edge. So had it been that the universe has a center, it will not be isotropic or homogeneous. So in this case, what we have understood from the principle, cosmological principle of what we have observed from our nearby environment is that the universe has no center and has no edge. It looks the same everywhere. So what this means is that there is no special location in the universe. There is nothing special about where you are. There is nothing special about where whatever other being is. So from this homogeneity and isotropy, no center, no edge, no privileged location, one can see that it has been in error, so to say, that for the bulk of the history of civilization, man has always assumed a special location in the universe. Usually he assumes the center stage in the scheme of things. So by the principle of cosmology, of this isotropy and homogeneity, then this assumption may not be true, because where you are is exactly looking like where other person or where other being is. So this idea of isotropy and homogeneity actually gave an insight into the possibility of having a life elsewhere, even beyond our galaxy. So because in the universe, if it is homogeneous and isotropic, and the objects are uniformly distributed, what it means is that the possibility of finding objects that are in similar environments like where we are is very high. And that is why it is often part of the studies in cosmology to look for extraterrestrial intelligence. So, but what we are trying to put across is that seeing the galaxies as the elementary building blocks of the universe, the cosmological principle is a property of the large-scale structure. It is a property of the large-scale universe, which looks much better the larger the scale you consider. Of course, when you try to look at a cosmological principle in local phenomena, you see that the cosmological principle will break down. For instance, if you look around you, wherever you are now, you see that things may not look isotropic and homogeneous. Why? Because you are looking at a small scale, which the cosmological principle cannot explain. So there is a very basic implication of this. If you look at this figure on the screen, is a picture of the night sky. And if you look at it, you see that the night sky is dark. Why? If the universe is isotropic and homogeneous, and there is a uniform distribution of luminous objects all over space, then why is it that at some point the sky becomes dark, at some other points the sky becomes bright? So this is actually an illusion that arises from, let me say, a kind of an erroneous impression which early scientists had in the past by assuming that the universe is static and objects in the universe are fixed in their position. So this contrast between the darkness of the night sky and the expected lit night sky, according to the distribution of luminous objects, was first put forward by Olbers. And that is what we commonly refer to as the Olbers paradox in cosmology. Not Olbers alone will be thinking about that. Many people may be questioning this as well. But along the line, we see how this Olbers paradox was partly explained. How did it happen? So because these objects are at varying distances in space, the idea of inverse square law relationship of flux with distance comes in. For instance, if you look at this equation, is equation describing the inverse square law in physics, which indicates that the radiation flux is inversely proportional to the square of the distance. So because of this, if the sun turns away from you and you are facing other luminous objects that are at much further distances, you find out that the radiation flux coming from them becomes much smaller because of the effect of the large distances. And as a result, the light coming from them will drop off and will not be able to give a light in the night. And that is partly an explanation to why the night sky is dark. So another simple explanation would be from the idea that objects such as these galaxies that are of interest in cosmology are redshifted. We will understand what this redshifting means as we go down. So they are redshifted and their radiation, which should be in the visible band, will fall off to lower frequency bands that are not visible. And as a result, optically, the night sky appears dark. However, the theory of cosmology hinges tightly to the theory of relativity, which was put forward by Albert Einstein in the early 1900s. Of course, between 1905 and 1915, Einstein introduced the theory of relativity, which is very, very important to us in modern cosmology. This relativity explains the dependence of various physical phenomena on relative motions of the observer and the object being observed. So especially regarding the nature and behavior of light, space, time, and very importantly, again, the effect of gravity. So it is this behavior that introduces the idea of Doppler shift of energy, which, as I said, some radiation may be redshifted and their effect will be observed at much lower wavelengths, much longer wavelengths. So relativity is concerned with the motion of bodies whose velocities approach the speed of light. Of course, we know that light is the fastest moving entity so far. Probably as we continue to search, maybe other things that will move with a speed, even with speed more than speed of light, may emerge much later. But for now, the fastest moving entity, as we know, is light. So when an object moves with a speed very close or getting closer to the speed of light, then we say that the object is moving with a relativistic velocity. So by implication, the theory of relativity has to do with objects that are moving with very high speeds, very close to the speed of light. And in this case, the total energy of such objects approaches the rest mass energy according to Einstein's equation of energy equal to mc squared. So when we look at these objects, if you are in space and you are observing these objects, one of the difficulties will be to ascertain how fast are these objects actually moving. And when that happens, you now see that if you are unable to determine to a very good approximation the velocities of these objects, some of the effects you are trying to understand will collapse. And then one may ask, you are looking at a galaxy in space, and you are telling us that it's moving with so speed or so velocity. How do you know that this object is actually moving with such a speed? So, and we explained that one can know that using the spectroscopic analysis of radiation coming from this object. As we know, the most common object in the universe is hydrogen, and hydrogen is characterized by a special spectral line, the 21 cm line. When it is in its neutral condition, the hydrogen atom emits a 21 cm line, which means it has an emission line whose wavelength is about 21 cm. But when we do the mapping of objects in the universe, we find out that this wavelength deviates significantly from 21. So 21 being the spectral line that is known could be used as a reference wavelength for determining other things about the moving object. So that gives us the idea of redshift, which is defined as equation 1. You can see lambda 0 there is the observed wavelength, lambda E is the emitted wavelength. So, and that gives the expression of the redshift, which is a Doppler effect. As we know from sound on Earth, you can easily observe this Doppler effect, but in space, Doppler effect in light can be observed. when the spectra of distant objects such as these galaxies are observed. So with this expression of the redshift and a little modification of Tully-Fisher relation, which we can see in equation 2, one can now use spectral analysis to get the redshift, and then with that relation that it is approximately V upon C, where V is the velocity of the moving object, one can make a coarse estimate of the velocity of the moving object. So in that case, we can now know how fast the object is moving, whether its speed is close or far away from the speed of light. So if you see this figure, you can see the idea of redshift and blue shift. When objects are moving away, the radiation coming from them, the wavelength is stretched, making it much longer. But when they are moving close to each other, the wavelength is compressed. So that is the idea of redshift. So in this case, as I try to explain, supposing we have the 21 cm line, which is exactly at 21.1, and we see an object that is emitting this 21 cm line, and by our observation, the line is observed at 21.6. After the analysis of the spectral line, the result can be used to determine both the redshift and velocity of the object using those equations. So that is the simple quiz I have put across here for people to understand actually how astronomers can make these estimations. And then from there, you see the casual solution I've produced, that in that case, the redshift parameter there is that 0.0237, and consequently, the velocity of such objects is 7.1 times 10 to the power 5 meters per second. So in this case, one can easily estimate the velocity of the objects. So in these relativistic terms, some of these important parameters could be the ratio of the speed of the object to the speed of light. And in that case, there is a relativistic factor, which is what we can see in equation 4. That's the relativistic factor from equation 3 to equation 4. We get the relativistic factor, which is used very often in cosmology to describe the motion of objects. And in this, because the light is the most fastest moving entity, these objects, when they are accelerated, they will move faster at a lower speed, but the speed appears fairly constant as it gets closer and closer to the speed of light. So the relationship between the velocity and the total energy of the body is what is presented in the figure as you see in the curve. So these relativistic effects give some noticeable observations, such as the time dilation, whereby in two moving frames, the time measured in two moving frames will differ significantly depending on the motion of the objects. So the equation for time dilation between one moving frame and another moving frame is given as this, where this gamma is that Doppler factor, as I have explained. There is also the length contraction, which is another effect of this relativistic effect. And the length contraction is expressed in terms of this. So between the one in observation frame and another observation frame that is in motion. So if we put side by side the Newton's idea of the universe and the Einstein's idea of the universe, the idea of force, gravitational force between objects, can be explained in terms of these effects of relativistic aberration arising from the fast-moving entities. So according to Newton, the force of gravity is there attracting two masses. But Einstein, in his theory of relativity, is trying to explain gravity in terms of the curvature of space-time. Take, for instance, I try to explain this idea of gravity and curvature of space-time, assuming on a very large spherical object, there are two small particles. Say there are two ants on a very big sphere, one at a point A, another one at point B. These two ants are unaware that that object where they are standing on has a curved surface. And then they set up to move up the page. So to the two ants, they appear to be moving parallel to each other. But Incidentally, because they are on that surface that is curved, you see that ordinarily, if they are moving parallel to each other and the surface is not curved, they will never meet. But because the surface is curved, they will intersect at a point, which means the paths will cross. So when you look at this figure, it tries to explain what gravitational attraction between two moving objects appears to Einstein, that the gravitational attraction between these two objects is a result of the curvature of the path of their motion. So in other words, that brings about the idea of a curvature of a space-time, which gives information about the geometry of the universe in which we live. So this now can show you that if, for instance, the curvature is the other way, when these objects are in motion, they can be moving away from each other. I know many of us have encountered this kind of figure, which is one of the basic observations in cosmology, which was made by Hubble. Of course, it was first made by Lemaitre and later on by Hubble, but it was Hubble that published it. And this relationship is credited to Hubble. It was just recently, about 3 or 4 years ago, that the IAU decided to credit this law also to Lemaitre, and then it became now a joint expression as Hubble-Lemaitre law. So Hubble observed this in 1929, using this spectral analysis, which I have tried to explain, to map the structure of galaxies in the nearby universe. And after that, he plotted the velocities of these objects against the distance. And this is what he saw. So from this data, you see that each dot represents a galaxy. As I said, the galaxies are the simple building blocks. The galaxies are the small objects in the universe. So each dot represents a galaxy, such a way that the vertical axis shows the velocity, while the horizontal axis shows the distance of that source or the galaxy from us. So from this, we see that from this axis, there is none of these objects located in a negative velocity. All of them have positive velocities. So, and positive velocity, as we know in physics, means that objects are moving away. Any object that has a positive velocity means it is moving away from you. But if it has a negative velocity, it means it is moving towards you. So one of the important observations of Hubble is that these velocities are all positive. And because of that, it is concluded that galaxies are moving away from us. So it's a fundamental observation by Hubble, and many cosmological problems and answers come from this simple observation. I was making a presentation yesterday, and I referred to this Hubble. Actually, it is this observation that ignited other theories of cosmology. And now, for the rest of the time I will talk, let us look at this simple observation and see how Hubble was able to derive some information from there. Look at the figure. I have grouped these objects, one in box A, the second group in box B. And I have posed a question for you so that you can also think about it and understand how Hubble was also thinking at that time. So which set of these galaxies, the one in box A or the one in box B, are closer to us? I know from your elementary knowledge of how to analyze a graphical distribution, one can actually determine which one is closer or which one is farther from us. So from this, your guess may be good as mine. You can see that the objects in box A are closer. Of course, if you look at the horizontal axis, the distance axis, for this object, their distances are just between 0 and 50 megaparsec. While for these ones, their distances range from 50 to 100. So the box A are closer to us than box B. So I look at another question, which will also enable us to understand what Hubble was doing. So which set or sets of galaxies are moving towards us? Of course, I have mentioned it. It's not likely that any of them is moving towards you or towards us because all the velocities are positive. So because all these velocities are positive, none of them is in the negative sense, none of them is around here, so all of them are positive from 0. So it means that there is none of them that is moving towards us. All of them are moving away. And that is how Hubble now discovered that all these objects are moving away from us. So, and then next set of questions, which set of galaxies are moving faster? Is it the set of galaxies in A or the galaxies in B that are moving faster? If you look at it, you see that the box in B are the objects there are higher up on the axis here. On average, they are around here on the velocity axis, while the box A, they are around somewhere here. So you see that objects in box B are moving faster. So this eventually gave rise to the Hubble's law that galaxies are moving away from us at velocities that are proportional to their distances from the observer. Now, in cosmology, we can now see from these simple illustrations and analysis that as far as we know, the universe has no center and has no edge. Why? Because of the isotropy and homogeneity of the universe. So there is no center to the universe, there is no edge of the universe. At least this is a take home for any person that is new in cosmology. There is no center to the universe, and as well, there is no privileged position. Where you are is as good as where any other being is in the universe. And as such, you cannot claim to be at the center of the universe. So the universe is not static, as has been the case in the early beginning of cosmology, where the objects in space are assumed to be static in configuration, and most beliefs then was centered on this idea of a static configuration of the universe. So from here, what Hubble has done has shown us that these galaxies are moving away. They are not static. So galaxies in the universe are receding from us. I am using the term moving away for us to understand, at least the layman can understand what it means when we talk about expansion. And this moving away is actually the reason for the use of the term expanding universe. So we will find out later that this expanding universe is simply an expansion of space. In other words, the distance between these galaxies are increasing, distances are increasing, space is expanding, and in the process of this expansion of space, the galaxies inside them are carried along with expansion. Probably when Professor Amabe comes in, he may be able to tell us more about this expansion. So we have also seen that distant galaxies are moving away faster than nearby galaxies. And this is actually that Hubble-Lohmeta law. Of course, most cosmology books will be calling it Hubble's law because they were written before this IAU verdict, which favored this joint expression of Hubble-Lohmeta. So, and as I said, on this Hubble's law, Hubble-Lohmeta law, which arises from that diagram of velocity and distance, on this law, the coerced answers to some fundamental questions in cosmology are embedded in, and they are answered partially from that single observation made by Hubble. For instance, one intriguing question that is bothering people's minds should be, how large is the universe? That Hubble's diagram will be able to explain to us how large it is. Then how old is the universe? When did this universe we are in, when did it start to exist in the form we know it? So how old is the universe is part of the questions that we will answer in cosmology that is also enshrined in that Hubble's diagram. Then how did the universe form? How did it begin? The concept of the origin of the universe is a hint on that, which probably by the time Amabe presents, he will explain to you that according to our cosmological knowledge so far, that the universe originated from a Big Bang, which is actually the Big Bang theory of the origin of the universe. Then the other basic question, which will always be fundamental to any person studying cosmology, will be, what will happen to it in the future? As we said, from the beginning, we look at our motion on Earth. There are two motions. We have the rotation of the Earth causing day and night. We have the revolution of the Earth causing the seasons of the year. This is one part. But the Earth also, as it revolves, it is going now with inside the solar system. And we are told in the study of galaxies that the solar system is also not stationary. Rather, it is moving about the galactic center. So this is a third motion now. So that motion about the galactic center, where you combine the effect of the motions of other objects, gives rise to what we often refer to as the galaxy rotation. Then now Hubble has now looked at this and came up with a fourth motion, that the galaxies are also not stationary. Instead, the galaxies are moving away. So one of the questions we will ask is, after all these motions, where are we going? So it means that we started somewhere and probably we are going somewhere. So this Hubble's diagram will be able to explain some of these fundamental problems, fundamental questions of cosmology. And on this note, as an introduction, as I said, this is actually how cosmological studies opened up. And I will bring in the second presenter to continue from there. Thank you for the attention given to this.
Thank you, Professor Do, for the talk. I think we may give about 5 minutes for question and answer before we call the next instructor. Okay, Ibrahim, go ahead with your question.
Good morning and afternoon, depending on the location. My question is, there are two. One is based on the expansion of the universe. I'll start with that one. Assuming one is observing two objects, the other one near the Earth, the other one away from the Earth. Now, looking at the shift, because the Earth is rotating, don't we have a possibility that the object that is far will appear to have moved further? Let's say we have drawn two circles, on the one on the near object, the other one on the further object. Is it not possible that the one which is further, after a shift from the on the Earth, will look to have moved further than the other one in terms of moving? Then the second question is on Ober's paradox. I think from the look of things, Ober must have been right to assume that the light can be observed, or the flux can be equal or the same if observed at all point on the issue of the dark night, or what it was supposed to be bright, whatever it is. But if using lower physics, I need clarification on that one. Using lower physics, there is a possibility. We know that there is matter, gas, and other matter in the atmosphere that is capable of blocking light. Now, assuming light is coming from a further source and it is being blocked up to an observer on Earth, there is a possibility that a lower amount of light will be received. I don't know if we have taken note of that, or I'm just thinking alone. For me, I have thought that the likelihood of obscurity, ionization, energy loss, and deflection might lead to the issue of dark night when the sun shifts away, because some light is being obscured, absorbed, and there is no way it can reach at the same amount. But without that, assuming it moved in a vacuum, there is a possibility that we can receive the same amount of light. I need clarification on that one, because it really confuses me when I look at the conclusions that are there. Of course, they are due to distance. The distance we look at, I don't see it as an issue. The issue is the light being blocked on the way. I don't know, I need clarification. That's what I've been thinking about when I came to learn about the issues of
Thank you,
Wolf's paradox
Ibrahim.
and the conclusion.
Yeah, thank you, Ibrahim, for the questions. Please, I would recommend that if you want to ask question, you at least make it a bit concise, because we don't have much time. Okay, Prof, over to you.
Let me respond starting from the last one, where you are talking about the Olbers paradox. And, of course, as I said, some people are also thinking the way Olber thought. But as I said, this Olbers paradox was put forward thinking that the universe is static, which means the objects in the sky are all static in their position. Of course, when you are standing on the earth and you look up the sky, even the sun, the moon, all those stars appear to be located at the same distance, erroneously thinking that they are located at the same distance from you. And that was actually part of why Olber was confused about the sun turning away its back to you and then the sky appearing dark. But what we are trying to present in this case is because these objects are not actually in the same distance away from you, when the sun, which is much closer, turns its back to you, you are now facing the objects that are much farther away from you. And even all those ones that are beyond the galaxy, not just that they are far away from you, but they are also moving away from you. So in that case, the radiation flux coming from these ones, which should have added up together to give you brightness in the night sky, will be shifting down. Of course, it will be falling off because of the large distances. That is the inverse square law, not actually a result of obscuration, but this fundamental issue of brightness and distance. Then the other one, as I said, is the other of the ones that are beyond the solar system, which should have added to the flux that will give the night sky its light. They are moving away, and the effect of the moving away will give rise to the redshifting of this radiation. Like this microwave background radiation that we encounter in modern cosmology these days, which is a proof of the idea of a Big Bang theory of the origin of the universe. This microwave background was emitted at a much higher energy, but incidentally, at the end of the day, it is observed at energy corresponding to a temperature of 2.7 K, which shows that its energy has fallen very much low to the microwave band. In other words, at the point of emission, the microwave background was not emitted as microwave. It was emitted as a much higher wave. So the same thing happens with the optical radiation that should come from these distant objects that are moving away. Instead of seeing it in the optical band, their radiation would fall to a frequency much lower than would be visible with the eye. Of course, that was what Olber was unable to grasp. So that is what explains the Olber's paradox. Then the second question, which was the first one you asked, I think I've even lost track of it. You said about...
Okay, I think he's talking about in case you are observing a system and the Earth is rotating.
Yes. So, yeah, if you look at that one, of course, in cosmology, we are not looking at what is happening on the Earth, because the Earth is inside the system which we see as a dot in the universe. So even the Earth that we are talking about as moving to the other side and then the object appearing closer, they all form a single object. We are trying to look at what happens inside the object, which is a local phenomenon. That's why we say that the cosmological principle will collapse when you are looking at local phenomena. because at that point, the effect of gravity and some other effects will be distorting what should be observed when you are looking at large-scale structures. So when we are talking about this, we are actually looking at large-scale structures which should actually be in a condition that the entire galaxy, which you have seen as a very large object, is forming a single dot in the universe.
Okay, thank you. I think to add to what you just said, if you are looking at what is within the local system, that is, maybe you are trying to observe stars, for instance, this is not a cosmological case. Then, but if you are trying to observe stars, for instance, which is located within a local system, there are occasions where the stars are not visible to the telescope. So the telescope has a particular field of view. And then based on the coordinates of the star, you can predict when that telescope can observe that star. And then you can set up the telescope in such a way that it will observe the star when the star is visible to that telescope. Probably tomorrow that we'll be dealing with observational astronomy, you'll hear more about some of those things. Okay, we have two more questions. Please, I want to plead with you to be very brief because in 5 minutes time, we'll be going to the next lecture. So Aman, go ahead.
Good afternoon, professors. So my 3 points, what I want to raise is, what did you mean when you said the universe is your own laboratory? By that part, my thing was unstable, but what did you mean when you said the universe is your own laboratory? And what is the difference between isotropic and a homogeneous? And what is radial velocity? Could you like define what cosmology is again? I didn't really understand the first time because my internet was unstable. But those are my 3 points.
Okay, as usual, I start from the last. Cosmology is the study, is astrophysics branch that studies the origin, the evolution or the history, and then the future of the universe. How the universe started, how it has evolved over time, and how it will be in a much later time. So that is actually the points of interest in cosmology. So isotropy and homogeneity. Isotropy means that in any direction you look, the direction is the same as any other direction, which means what you see in the eastern direction, according to your location, is what you are going to see in the western direction, is what you are going to see in the northern direction, is what you are going to see up, or what you are going to see down. In any direction you look, you observe similar things. That is isotropy. Homogeneity. The matter content distribution is uniform. Just like when you look at water, for instance, we say water is a homogeneous liquid, which means what you see at one point of that water is what you see at another point. The density of the water is uniform. The matter content is uniformly distributed. That is the idea of a homogeneity. And that is what we say that when in cosmology, especially when you are looking at large-scale structures, the structures in the universe are homogeneous, which means the system is uniform in matter distribution. The system looks the same in every direction. That is the concept of homogeneity and isotropy. Then we say that the universe is our laboratory because we are making observation of the entire universe, everything we can see in the universe. So we don't have a room where you go to start making observation inside the room. What you see is what you see outside the space. So the entire universe, all the galaxies that you can see, everything you can see in the universe is part of what we are using to make predictions about what the universe is. So that is what I mean by the entire universe being our laboratory. So we are not limited to the earthly laboratory where you go inside one room and use one instrument to start looking at it. We are looking at the entire universe as a system. So that is why in that case, these galaxies are seen as point particles in the universe. Just as you have a cylinder containing a gas, the cylinder contains gas, and these particles, gas particles, are the point particles that are being used in studying the behavior of the gas. So in this case, the galaxies are used to study the behavior of the universe on the large scale. Thank you.
Thank
And
you.
you didn't define what radial velocity was. I mentioned that earlier.
Radial velocity. Radial velocity means the velocity with which an object is moving away or receding from you, either receding or approaching. Right? The velocity with which an object is receding from you or approaching you is what we refer to as the radial velocity in cosmology. Thank you.
Thank you, professors.
Okay, the last question we'll take here. Please, I would those questions we have on Slack, I will would like to encourage you to send it to Slack, please. The question we have on chat here on Zoom, please send it to Slack. He will attend to it then. Or probably if we have time by the end of the second lecture, we might still take them. So the final question is from Gospel. Gospel, go ahead with your question.
Okay, I hope you can hear me clearly. So,
we can't hear you if you're talking.
Can you hear me? Can you hear me? Okay, sir. My question.
Gospel? Okay. I think we can move on with the next lecture since we can't hear him. You can send your question to Slack or maybe ask the question after the second lecture. So,
okay.
Professor, maybe you introduce the second lecturer.
Hello,
Okay.
can you people hear me? Hello? Hello?
Yes, we can hear you.
Okay, Christian, thank you for the moderation, Professor. I'm in far remote area now, joining you people. There is a question that Ibrahim asked about obstruction. So in this sense, that doesn't even exist, because when a matter is absorbing radiation, at a point it will start re-emitting. So the issue of object blocking radiation in cosmology is not feasible. And in cosmology, actually, we are dealing with large-scale structure. So the solar system is not even a point of reference in cosmology. So people shouldn't confuse cosmological concept with terrestrial phenomena. That's the only thing I want to contribute. I'm having network challenges here. Thank you.
Yeah, thank you very much for the additional clarification. Yeah.
Okay. Thank you once again. Now I introduce the second speaker on this topic of cosmology. And here I am introducing Professor Amare Abebe. Professor Amare Abebe is a professor of astrophysics and cosmology and the director of the Center for Space Research at the Northwest University, South Africa. So he will take the rest of the lecture on cosmology. So Professor Amare, you are welcome to the presentation.
Right, thanks, Simba. Can you hear me?
Yes.
Yes.
Right, great. Thanks for inviting me to give this lecture, and I will focus on some of the aspects of cosmology that Simba has not necessarily covered in detail, but he said quite a lot of interesting things that will be useful for this lecture. Okay, let me try to share my screen. It works this way. Okay. You see my screen, I hope?
Yes, we can see it now.
Right, great, thank you. So what I want to talk about is basically this three things to just summarize more on what the universe entails and in relation to us especially. That requires some description of gravity, and I'll talk about what gravity is and why it is needed in the study of cosmology. And then I'll talk about the standard cosmological model that describe the evolution of the universe, how the initial conditions are set up, some exact solutions, and then some cosmography, distancing cosmology. And then I will talk about some of the limitations of the standard cosmological model and provide some suggested solutions that are available in the literature. Okay, so Simba has already described the homogeneous and isotropic nature of the universe. This is just to give some perspective on what our local environment looks like. He mentioned that we are not at the center, as you can see here also. This is the Milky Way galaxy, and the Milky Way galaxy is just one average galaxy of all the hundreds of billions of galaxies that are out there in the universe. And we are the solar system, right? And the solar system is not at the center of the year. It's not, the sun is not one of the biggest stars, never mind being at the center. It's basically an average star, right? And in the solar system, we are not at the center of the solar system either. We are somewhere, the third from the center, right? So even if we look at things on a local scale, we are not anywhere close to being the center of anything. And the largest scheme of things, of course, you've heard already that there is no center of the universe to talk about. Now the question is, this is probably one of the, if you attended some talks of cosmology, this is probably one of the most famous pictures you might have seen, especially in the last decade or so. It briefly gives you the timeline of the evolution of the universe that started off at a Big Bang, okay, right there. And see here, and just a tiny fraction of seconds after the Big Bang, the universe underwent some exponential phase of expansion called inflation that would seed the future large-scale structures that would eventually form in the late universe through this mechanism of quantum fluctuation. So we're looking at structures at this point here. And then after the end of inflation, the universe starts to cool down. Structures, first of all, those elementary particles start to form, and then we pass through this so-called dark ages of the universe, and then a matter-dominated phase around here, where all the major large-scale structures formed. And then at the moment we are in a dark energy-dominated epoch, where the universe is undergoing not only an expansion, but a second phase of accelerated expansion. We've seen the first phase that happened just moments after the Big Bang. And at the moment, we're also going through another phase of expansion, which is accelerated. And that's believed to be due to some form of energy called dark energy, but I will briefly describe about what other alternatives we also have to this. And based on this, it is estimated through theoretical calculations and observational data and all that, that at the moment the universe is about 13.8 billion years. So you already have been introduced to this idea of cosmology, what it is. In the wider sense, of course, it is a discipline as old as mankind itself, because we have always wondered about our origin, where we come from, how what the universe looks like, what happens to it in the future, and so forth. In fact, the word cosmology itself comes from a Greek word, cosmos, which means an ordered whole, as opposed to chaos. Okay, chaos and cosmos are opposites in Greek philosophy, and chaos simply means the disordered void that preceded the creation of the universe, whereas cosmos is the one that is the ordered whole. And cosmology would be the study of the universe, study of that ordered whole. Strictly speaking, when we talk about physical cosmology, modern cosmology, we differentiate it from the mythology that went before it and the philosophical approach of doing things, because now we involve physics, we involve the scientific principle, which is based on an evidence-based knowledge creation, right? And in science, you need to have testable and reproducible explanations and predictions of things. And this aspect of cosmology started, as you've already been told earlier as well, by the formulation of the general theory of relativity by Einstein in the early 20th century, about 100 years ago. And it mainly concerns itself being a scientific discipline about the scientific origin, the large-scale structure formation, the evolution, and the ultimate fate of the universe as a whole. And it deals, you can answer questions like, how did it originate? How large is it? What is the geometry? What is the topology of the universe? And how old is it? How can you calculate the age of the universe? And given the current conditions, can we say something about what will happen to it in the future? Will it expand forever? If so, in what way? In an accelerated way, or in some decelerated form, or the constant expansion rate? If not, will that expansion stop somewhere, and so forth? So we'll try to also discuss this kind of things in the theoretical aspect of the course when we deal with it. So I mentioned that the general theory of relativity was formulated about 100 years ago. And around that time, when people talked about the universe, it was assumed that it was some kind of static structure that existed and will exist as is, no change in its overall structure. In other words, when Einstein's general theory of relativity predicted that the solutions imply an expanding universe, people like Einstein were stunned, and they actually resisted this prediction. Mainly because at that time, the universe, all the known reaches of the universe didn't go beyond the Milky Way. So the Milky Way galaxy was all the universe people knew at the time. Only if a decade or so later for us to realize that there are Milky Way-like structures out there. And what do we know about the universe today? Now we know that there are about 100 billion galaxies in the universe. I mentioned earlier that the Milky Way galaxy is just one of those average galaxies, not even the largest, it's not the smallest, an average size. And there are about 100 billion galaxies. Some of them bigger than our Milky Way galaxies. And each one of them have, on average, about 100 billion stars in them. So our Milky Way galaxies, believed to have something close to 100 billion stars. So you can imagine the immensity of the universe, the observable part of the universe, should I stress at that. And at the moment, the temperature, the universe has cooled down so much since the Big Bang that at the moment it is literally the coldest place in the universe at a temperature of about 0.7 Kelvin. And if one measures the physical extent of the universe, it's about 92 billion light years across. So if you measure, this is just a hypothetical center. Of course, we say there is no center. So if you measure from here to here, that's about 92 billion light years. And you might ask yourself, okay, how is that possible? Because if you assume the age of the universe is, let's say 14 billion years, earlier I said 13.8, for simplicity's sake, 14 billion, right? And assuming that it started expanding from here until it reaches here now, that would be about 14 billion years that a photon could travel, the fastest that any particle can travel, right? So from here to here, that's 14 billion, and you'd expect from here to here to be twice of that, so about 28 billion light years across, right? So what is happening here? Does anyone want to comment on this? How is that possible? Okay, we'll get back to it when we talk about the actual expansion history, and you'll realize why this could happen. Then I mentioned modern cosmology started with the formulation of the general theory of relativity, which, by the way, is a theory of gravity, the generalization of Newtonian gravitational theory. Now the question is why? Why the obsession with gravity when we talk about the universe? We know that there are several forces of nature, actually four to be precise. There's a strong interaction, which is by far the strongest of all the four forces, about 10 to the 39 times stronger than gravity, as you can see, right? If you compare the relative strength of gravity and the strong interaction, the strong interaction is about 10 to the 38 times bigger. And you can actually see that gravity is the weakest of all the four forces. So in the presence of all these three other stronger forces, why do we care so much about gravity? Anyone? It would be nice if we could interact in this during this lecture. Anyone has a guess on why we only focus? Yes, Aman.
Oh, right. You're saying gravity, the strength of gravity. I think it's like that because gravity is spread out throughout the universe and that it has a particle which helps with link with quantum gravity, which explains the universe.
Okay, so my question is, when we talk about cosmological evolution, we mostly focus on the effect of gravity on the evolution. We don't care so much on the weak interaction and the electromagnetic interaction and the strong interaction. Why do you think that?
Well, I think we don't focus on electromagnetic and weak because they're not really a major part, while gravity is a major part of the universe and like is what attracts and formations of the universe, which links to theories like quantum gravity.
All right, let's hear what Inyama has to say. And there's also someone else. Yeah, Inyama, can we start with you?
All right, can you get me?
Yes.
So I think it's because of the range it has. But looking at the other three here, they have quite a small range. I mean, the other two rather. But gravity has a wider range, and also it deals with mass. So the objects we're dealing with are quite massive. So that's why I think it is more useful in cosmology.
All right. Okay. Thanks for that. Who else? Nigis. Hi.
Hi, Amix.
Hi.
So
Yeah.
if
You've heard the other answers. What extra that needs to be added?
if we are talking about the three forces, we experience them in the Earth's atmospheric layer. So if we go farther from our atmospheric layer, the force which we experience is the gravitational force. I think so. I mean, it will be neutralized as we go further from the atmospheric layer. So, the force which we experience outside the atmospheric layer is the gravitational force. I think that is the reason why we focused on gravitational force.
All right, thanks. Is there another hand there? Let's see. There's some other hand, please speak up. So these were the only hands I saw. Yeah, I think most of you have, well, let me say all of you have touched on some aspect of the answers. For example, some of you commented that gravity has a long range in some sense, and the other ones have short range and stuff. True, it's true for the strong and weak interactions, which are only applicable on subatomic scale. Their range is subatomic. But the electromagnetic interaction has the same range as the gravitational force, but you guys didn't mention why the electromagnetic force is not important, although we see that it's much stronger than the gravitational field. And the main reason for why the electromagnetic field does not, interaction rather, does not play a major role in the evolution is that the universe overall is neutral. So the forces cancel out, although one can imagine that the electromagnetic force would play a role. Overall, because of the overall neutrality of the universe, these forces do not play a role in the evolution of the universe. So that leaves gravity the only force, although it's the weakest of all of them, the only force that plays the role of evolution. So now we've talked about gravity, but what it is. So that is where we can, go back in history and see how people have perceived the nature of the world and even the idea of gravity and so forth. So you might have received the slides already at some point, somewhere uploaded somewhere on the platform, so you can read about this. You are interested in the historical aspect, but what I would like to mention is that our understanding of the nature of things in the universe itself, the force of interaction, gravitational force in general, in particular, have evolved over time. And we are now at a point where we can say, oh, there's actually no such thing as a gravitational field or interaction. There's simply this idea of the curvature of space-time that forces things to move around that center of curvature. Whereas in Newton's time, one would assume that because of the existence of two mass bodies, there is some kind of fictitious force field that exists that makes this attraction between the bodies. Before Newton, if you ask people about 1,000 years ago why things fall, for example, at the center of the Earth, they would refer to Aristotle's law, which is basically that things fall toward the center of the Earth because the Earth is home of all things. So the things are falling down, going back to their natural abode, natural home. So things would fall to a gravitational field that we call during Newton's time, or the center of curvature in Einstein's interpretation. But in Aristotle's view, they were just going home. Okay. Yes, Christian.
Okay, Prof, I think we usually have a break period at 12:15. Maybe we can extend it to 12:20 and reconvene again at 12:45.
12:45. Okay, that works for me.
Okay, that's fine. So by 12:20 watts, you can give them break, and then we reconvene at 12:45.
All right, cool.
Thank you very much. Yeah.
All right, so that's basically what the modern interpretation of gravity is as a curvature of space-time. But when one talks about the curvature, then there are also three possible interpretations, geometrical interpretations of curvature. And this would come in the form of this so-called Riemannian description. Yeah, Riemannian curvature. There is also this idea of torsion, and there is this idea of non-metricity. So I will just briefly mention that when one talks about Riemannian curvature, that's basically the if you go around, if you parallel transport a vector around a loop in a flat Euclidean geometry, you would expect that vector, if you're transporting this one along this loop, you would expect it to come back to the original position. But the failure of that vector from aligning itself to the original direction represents this so-called Riemannian curvature. That is one way of looking at things. And this is exactly the foundation on which general relativity is based. Einstein's general relativity uses Riemannian geometry. Einstein did consider another way of looking at gravity through this so-called torsion. And that is, if you have two vectors that we did in high school and first year physics, you have two vectors and you want to add them, you assume that you can form a parallelogram. You can close the parallelogram by bringing this one here, bringing this one there. That assumes that in flat space, when you parallel transport this vector, it's aligned in such a way that it closes that parallelogram. The same for this one. But the non-closure of this parallelogram is what introduces this idea of space-time torsion. And there is a formulation of gravity based on this torsion. In fact, Einstein worked on what was referred to as the teleparallel equivalent of general relativity. At the time, we're talking about 1928 or so, around that time. When Einstein tried a different approach to formulating gravity, he realized that the field equations that he got were equivalent to general relativity, and there was no prediction power of this theory that's different from general relativity. So it was abandoned. But it was referred to as the teleparallel equivalent of general. The other thing is when you, again, transport a vector along a curve, you assume that that vector maintains the direction and the length the same. But if the variation of the length of the vector is affected, if the vector does not have the same length anymore when you transport along a curve, you introduce what we call a non-metricity. And there is another formulation of gravity based on this. And some of those modified theories of gravity that you might have heard of, or that I will mention in a while, are based on these three different ways of looking at gravitational curvature, space-time curvature. So there's GR, there's teleparallel equivalent gravity, there's this symmetric teleparallel equivalent gravity, which is based on electricity. And GR introduces a scalar in the action, which we call the Ricci scalar. Here, in the case of teleparallelism, we have this torsion scalar, and in the case of this non-metricity, we have this metricity scalar that show up in the action from which the equations would be derived. I think that is basically what I want to say about gravity in our notion of the universe in general. And from now on, I'm going to talk about the standard cosmic prediction model, some of its predictions and some of its shortcomings. And I think this is the right time to stop for that short break and come back at 45, 12:45.
Yeah, at 12:45, yes.
Yes.
That's in
Thank
24-minute time now, yes.
All right, yeah, thanks so much.
Thank you. So you have 24 minutes break and you come back for the continuation of the lecture. Hello, everyone. Professor
Hello.
Mer, I think you can start now. This is
All right.
12:45.
All right. Thanks, Christian. Okay, so from now on, we're going to talk about the standard cosmological model and then some of its shortcomings. So we said earlier that the physical cosmology took its roots in the general theory of relativity. The Einstein field equations predicted an expanding universe, and this was realized as early as 1917, which is about 2 years after the theory was formulated. So when that happened, it was quite a puzzle, as I mentioned earlier as well. But what do we mean by expanding? So I've put these balloons just as a pedagogical illustration. And you have one balloon there, you inflate it, becomes bigger, and inflate, becomes bigger, and so on. So if you put two dots on the balloon, like let's say this dot here and this dot here, and as you keep inflating, the dots become further and further apart from each other. And visualizing this as the universe and the dots as two galaxies, then you think that if any pair of galaxies is having this kind of situation where the dots are getting further, then the natural conclusion to come up with is that the universe itself, the balloon itself, should be expanding. And that's basically how we came to conclude that the universe must be expanding. And later observationally confirmed that that must happen. So when just before the observational confirmation in the late 1920s, when Einstein discovered that his theory predicted an expanding universe, he actually introduced something to stop that expansion, which is now referred to as the Einstein constant. This lambda term that you see there is that constant introduced as by hand, basically, to stop the expansion. And when this whole idea of a static universe was, disproven by the observational evidence of expansion, he is said to have called it the biggest blunder of his academic career. But you'll see later that we have brought this term back into the equations for a completely different reason, the opposite reason, if you will. Initially, it was introduced to counter expansion and create a static universe. It was forgotten for decades because of the confirmation of observation. But since the late 1990s, it has been brought back to the equations again, because we need it for explaining the accelerated expansion. Very ironic, but that's basically what's happening. So the observational confirmation happened in the form of Hubble's 1929 data, which measured recession velocities of galaxies versus distance. And you'll see this kind of relationship where the farther away pairs of galaxies are, the faster in general they're receding from each other. This is an average conclusion. There is some exception to this. For example, the Andromeda and the Milky Way galaxy in our local group are moving towards each other as opposed to moving away from each other. And that's because of their physical proximity and the expansion rate being slowed down by the gravitational pull. So there's always a competition between gravitational forces, the space-time curvature manifestation that we mentioned earlier, trying to bring structures together, and the expansion trying to push them apart. And if the gravitational interaction is stronger, then it can happen that some galaxies might move towards each other because of peculiar velocities. rather than because of local contraction of the universe. So there is that. So on average, every pair of galaxies in the universe is moving away from. So if the universe is expanding, and we know that's of a certain finite size today, what does that mean? It means that if you run the clock back in time, it must have been smaller and smaller and smaller and smaller. And at a time, at an initial time t naught, let's say t naught equals 0, in this case, the Big Bang time, it must have been of infinitesimal volume and of infinite density, basically, because, you know, if the total matter in the universe is conserved, the total energy is conserved, total energy rather than matter, then, you know, at the moment there is a certain energy density rho, which is energy per unit volume. And if the volume gets smaller and smaller for a conserved energy, this one must be bigger and bigger. So if you run back in time and the volume of the universe is smaller and smaller, at the point where this one is infinitesimal, this one becomes, and that's infinite density, extremely high temperature, nearly zero volume structure of the universe is what we normally refer to as the Big Bang. That which, you know, starts to expand pre-inflationary epoch that I mentioned earlier, and has set this expansion, supposedly non-ending expansion, according to standard cosmology at least, and has led to all the large-scale structure, all the elementary particles that formed just seconds after the Big Bang, first few minutes of the Big Bang, the radiation and matter-dominated epochs that I mentioned, the dark energy. And according to current data, this must have happened 13.8 billion years ago to explain all the structures that we have. The idea of the Big Bang was, of course, not accepted by everybody. There were competing theories, the most famous of them being the so-called steady-state theory. So between the 1920s and the 1960s, there was a big rivalry between, you know, the steady-state and the Big Bang theory. And the debate was so fierce that one of the proponents of the steady-state theory kind of angrily said that, you know, so you're saying that the universe somehow started in a Big Bang, you know? So he didn't mean it to stick as the standard theory of our cosmological evolution at the moment. He was saying it in a derisive manner. But that's what has been so catchy that, you know, the actual proponents of the Big Bang theory ended up having this term coined for them rather than the steady-state theory. The steady-state theory maintained that the universe was, is, and has, and will always be the same in its internal, you know, structure and evolutionary history. So it has not changed in its, you know, distribution of structures and so forth. So it had a predictive power in a sense, but then when you have two competing theories that are vying for dominance, the one thing that always favors a theory over another is the prediction power. If a theory predicts something and the prediction happens to be true, then that theory passes to the next stage. It doesn't mean that that theory is the ultimate theory. It simply means that it passes to the next stage of verification. But if another theory fails to predict that, does not predict that, it means that theory, although it is a good theory, is falsified by virtue of the prediction that the other theory, theory B, if you want. So you have, this is theory B, this is theory A. Theory B predicted that after the Big Bang, there must have been some kind of radiation that permits the universe which we now call the cosmic microwave background. And theory A, the steady state theory, could not have predicted that. So when the moment that CMB was discovered, CMB in the 1960s, around 1964-5, when this was discovered, then this theory could only explain that. It had predicted it and it explains it. This theory did not predict that and it failed, basically. So the 1960s was basically the last time this steady state theory was taken seriously, and the Big Bang theory became the ultimate theory that explained the evolution. So as you can see in the Big Bang model, you have a certain amount of energy in the universe which as the universe expands becomes less and less dense. And the steady state model, that energy density does not change. Supposedly there's some kind of matter that gets created into existence and then neutralizes the expansion in a sense, that the dilution of the energy density. It remains in a constant steady state as the universe expands. So one of the predictions, as I mentioned, of the Big Bang theory that ultimately made it the main component of the expansion history of the universe was the prediction of the CMB. The CMB today is of a temperature of 2.7, as we mentioned earlier also. It looks on very large scales, it looks homogeneous and isotropic on all scales. By the way, the word on large scale, the phrase on large scales is very important because as you can see, some of you were asking about solar system, Earth scales, physics. And in those small scales, the solar system is considered a small scale. Even the galactic scale is considered small scale on cosmological scale. On small scale, we are not claiming that the universe is homogeneous and isotropic. Because if you look at something in our local sky at night, you see in one direction, you see some kind of group of stars there. See another one, you see another group of stars, and so forth. The distribution is not uniform and it's not isotropic. But on the very large scale, and by the very large scales, we're talking about something like more than 100 megaparsec and above, extragalactic scales, basically, then the distribution of structures looks more or less the same. And if you look at the CMB today, on large scales, it is uniform, isotropic, homogeneous, but there are fluctuations that are of the order of 1 in 10,000, 10 to the minus 5 fluctuations in the temperature and the overall structure distribution. So what controls the expansion? I mentioned earlier there's this constant fight between gravity and expansion. And depending on which one wins, eventually, the fate of the universe will be determined. And what determines this is actually the density of the energy density of the universe. There is so much energy density, there is so much matter in the universe, then it tends to curve the universe. If there is less matter distribution, it tends to flatten out. So based on this, there are 3 different possible cases that one can talk for the geometry. Sorry. And these are when there is more matter than a certain critical energy density, we have a universe that is closed. If there is just enough matter to counterbalance the expansion, then that results in a flat universe, like a tabletop. And if there is subcritical distribution of matter, we have an open universe. And depending on whether the universe is closed, flat, closed, flat, or open, the expansion history will be determined. And in the case of a closed universe, the universe will expand from a Big Bang, reach a certain maximum size, and the gravitational pull will be winning over the expansion and then starts contract and eventually end up in a big crunch. If the universe is flat, which, by the way, the current standard cosmological model predicts that the universe is almost flat, then the universe expands forever, but approaching a certain asymptotic size in the far future. If the universe is open, where the curvature is negative, then the universe expands faster and faster and faster over time, and eventually end up in a certain catastrophic scenario called the heat death, the big chill, they call it in different heat death or thermodynamic death. So that's that. What is the geometry of the universe? Is one of the questions cosmology concern itself with. And according to the standard cosmological model, a homogeneous and isotropic expanding universe is described by this kind of metric, space-time metric, which is called the Freeman-Lemaitre-Robert geometry. And depending on the curvature signs, you can actually fix the full space-time metric explicitly. The rate of expansion of the universe is given by this parameter called the Hubble parameter. It tells you the normalized rate of expansion. So A is the size of the universe at a given time, not in physical terms, but in scale terms, the scale. So if the universe is of size 1 now and it becomes 2 tomorrow, then and then after a while it becomes 3, just in relative terms, tells you that the universe is getting bigger and bigger. But if it's 3 and then 2 and then 1 in size, in relative terms, I'm not saying in physical terms, then it tells you that the universe is getting smaller. And the parameter that defines this is this scale factor, which depends only on time because we're assuming homogeneous and expansion. Another important parameter is the redshift that you have been introduced to earlier as well. Tells you whether something is coming towards you, blue shifting, or going away from you, red shifting. And there is some relationship between the scale factor and the redshift given by this equation. And one of the things that is usually given as an exercise for introductory level cosmology is to actually show that for small redshift, there is a linear relationship between the recession velocity of galaxies that we saw earlier in the Hubble diagram and the distance between the particular galaxies, and the parameter that's considered the proportionality constant is called the Hubble constant. So this law used to be called the Hubble law in the past, and as of recently, as you heard earlier, referred to as the Hubble-Lemaitre law because of Lemaitre's contribution to this idea of Big Bang-based universe. So knowing the Hubble constant is one of the most important things in cosmology, because if you know the Hubble constant, you can tell quite a lot of things. You can tell about the size, the age, and several other cosmological parameters you want to know about the universe. And its SI unit is supposed to be in per second because H was defined as so earlier as A dot by A. A has no dimension, and dot is differentiating something with respect to cosmological time, and so that has the dimension of 1 per time. So it's measured in per second. But because of the large scale of numbers involved in cosmology, writing something like, H naught is of the order of 10 to the minus 18 per second, instead of writing a small number like this, we usually measure it in something called kilometers per second per megaparsec, where a megaparsec is just a million parsecs, and a parsec in astronomy, as you might already know, is this many light years, 3.26 light years, and in terms of meters, you can express it. So it tells you how fast two galaxies that are 1 megaparsec away are receding from each other. So it basically is, the speed at which two galaxies that are fixed at a distance of 1 megaparsec are moving away from each other. That's why it has a kilometer per second per megaparsec. And the initial value that Hubble predicted was about this number, 500 kilometers per second per megaparsec. And if you use this in standard cosmology to calculate the age of the universe, you would get a very small number for the age of the universe, because the bigger the value of h naught, the smaller the age. You'll be asked, we'll see in a moment why. There is a proportion, an inverse proportionality between t naught, the age of the universe, and the double parameter h sum. So it was this number, but recently measurements have become more and more accurate, and we are hovering around a value of between 65 and 75. So if you look at the most recent values of h naught, are they not here? Yeah, they are here. We're talking something about 67 there, according to this observer, for example, something like this 73, according to this measurements, and so forth. So there is some kind of observational tension between the measurements as well, which I will briefly mention the next few minutes. But the value of h naught today is far from the 500 kilometers per second that Hubble per mega parsec that Hubble predicted about 100 years. All right, so the dynamics. In terms of the dynamics, we assume that the universe is, of course, described, the geometry is described by the Einstein tensor, which describe the geometry of the space-time, and then it's filled with some kind of matter which is characterized by the energy momentum tensor according to this quantity here. I'm not going to go into details. If you guys are interested, you can take a look at that, but we call it a second order tensor that's symmetric and involves this energy density and pressure terms for velocities of fundamental observers. And this is, of course, the geometry on which the whole thing, space-time scenario is based. And then this is a divergence-less quantity, so you can calculate how the energy density of the universe evolves over time. You can see that because of the energy density differential with respect to time becomes the negative of this term here, if you put it on the other side, and theta expresses expansion, the volume expansion, you see that d mu by dt is something of the order of mu plus p times theta. And this is expansion. You would expect that as the universe expands, the density decreases, and that's exactly what this negative sign is. And you can actually solve this for specific cases, and in that case, you have some kind of relationship between the energy density and the pressure of matter, given by this equation. And if you consider W to be constant for a specific type of matter in the universe, you can solve that evolution equation of the energy density. And for different types of matter, you can get different. For example, for pressureless matter, like baryonic matter and dark matter that I will mention what it is soon, the energy density decreases as 1 over A cubed, where A is that scale factor. For radiation type of matter, it has A to the minus 4 ratio. For a cosmological constant, then the relationship between P and the energy density and the pressure is such that pressure should be the negative of the energy. And this kind of fluid can actually produce an accelerated expansion. So there are some exercises that I want you guys to also look at after the lecture when we get the slide. So the expansion history is described by this so-called Friedman equations. You have the equation that describes how the scale factor changes over time, and as you can see, the rate at which the scale factor changes depends on the energy density present in the curvature of the universe there. And then there's also another equation that describes how fast that expansion is happening. And this is called the acceleration equation, part of the Friedman equations, but it has also a specific name called the Raychaudhuri equation. And it's actually the second derivative of the scale factor. The second derivative of the scale factor is positive, shows that the expansion is increasing, because the first derivative has to be greater than 0. And if the second derivative is negative, it means the expansion is decreasing over time. And for quite a while, from the 1920s, since the expansion was confirmed, till the 1990s, like about 20 plus years ago, cosmologists were under the impression that because of the fact that this term is positive and this term is positive for normal types of matter, and this term was removed, you remember, then A double dot has to be negative. And that implied that the universe was decelerating. And that was all the assumptions made for several decades. Until in 1998, two teams of independent observers showed that based on the observations they made on supernovae, the expansion must be speeding up, meaning that this quantity, rather than being negative, should be positive. That's the implication that they got from the data analysis. And now people had to scramble to come and explain how this could be. And that's when some of the easiest alternatives produced was to keep that lambda that we threw out earlier because of the confirmation of the expansion. If you have lambda, if lambda is dominating over these negative terms, it means A double dot can still remain positive. And this lambda that was reintroduced to explain an accelerated expansion, they called it dark energy because one, it must be a form of energy because it's pushing the expansion faster, and not form of matter, which tends to cluster and reduce the expansion. And two, the word dark was just used as a way of saying that we don't know what it is. We cannot see it in the electromagnetic spectrum, and we cannot detect it directly. So let's call it dark. And this term is called dark energy. In order for you to have a dark energy kind of scenario, you must have this, if you do not want a lambda to appear here separately. So even if you have this kind of equation without a lambda, then you must have this term negative, and that implies the equation of state parameter has to be bigger than a minus. And the deceleration parameter is usually defined in such a way that incorporates deceleration there, because that was the initial assumption we had, and it's defined in a dimensionless way according to this relation. So if you hear about me talking about the deceleration parameter, that's basically what. So now we have those coupled system of equations, and in order for us to be able to solve them and make sense of them, we should of course have some kind of initial condition. And the way you can set an initial condition for a set of differential equations is, you set the time t naught that's convenient to you. And for us, it looks more logical to say, okay, let's assume that the expansion rate today is this much because we can measure it using different observational techniques. So we set the time t naught as today and measure the Hubble parameter as h naught. If you know that, then you can work backwards and find all the other parameters that you need in terms of the energy content, which are fractional quantities defined in terms of the Hubble parameter here, or the deceleration parameter, the today value of the deceleration parameter. You can calculate those things. So the way we set up the initial condition is based on our own circumstance of where we know things better. So if you know some quantity very well, better than today, for example, during the radiation-dominated epoch, easier for you to set your initial condition there and evolve backwards or forwards. Forwards meaning towards now, or backwards towards the big bang. So, and once you have the initial conditions, of course, you must have a unique expansion history because you have a unique solution for your differential. If you have not fixed your initial conditions, meaning you have integration constants that can take any value, then you don't have exact solutions. You don't have unique solutions, but several possible solutions for your cosmology. So once you fix your initial conditions, your evolution history of the universe is fixed anyway. All right. So depending on the geometry and the initial conditions that you set up, you can then find some exact solutions for different scenarios. For example, you might consider, oh, there's no dark energy, but something else that causes the expansion history, for example. And then what kind of exact solution can I get? So for lambda equals 0 case, you can find exact solutions for a curvature free, meaning flat, or an open universe or a closed universe. Depending on which geometry you have, you can calculate all the different scenarios. For example, you see that for lambda equals 0, if the curvature is 0, then you have a forever expanding universe scenario that we saw earlier. If the curvature is positive, we saw earlier in that diagram where we have a Big Bang and a Big Crunch kind of thing, that if there is no cosmological constant and you have a closed universe, the universe collapses to a future singularity that we call the Big Crunch, and so forth. So there are several cases which I do not have the time to go through that you can obtain depending on the consideration you get. If lambda is negative, lambda is positive, lambda is 0, and so forth. So I want you to go through this and show some of these claims that I have made in terms of the good solution. The other thing very important in cosmology is this so-called cosmography, which is basically measuring the distance between two cosmological objects. And measuring things in cosmology, distance in particular, is very tricky because the moment, first of all, you cannot measure distance directly because you're not going to use a ruler or a metric stick to measure distance because of the huge magnitude involved, right? And the other thing that makes it complicated is the fact that the universe is expanding. So the universe is expanding and the geometry is not Euclidean. So there is curvature involved and there is expansion involved. So the things that we measure in terms of distances are very tricky, and as a result, there are several definitions for distances that you can look up and see what makes sense. Jesus. Is that, and one of the things that I mentioned earlier is the cosmological redshift. The larger your redshift, the deeper into the history of the universe you are looking at. And today, if you look at this definition, and A at T naught simply means the scale factor today, which we usually set as 1. And then we have this so-called 1 plus Z plus 1 over A relationship, where A is a scale factor and this is a redshift. So you see some kind of inverse relationship in a sense between redshift and scale factor. So when the redshift is 0, we're talking about today. Okay. And when the redshift is big, it means the scale factor is very small, which means the size of the universe was very small, and it means we're talking about something that far past. And at the Big Bang, you see that the scale factor is supposedly 0, and the redshift should be infinite. So there is that. So based on this, what do we know about standard cosmology? So we say that the universe started off as a very dense and extremely small and hot state called the hot Big Bang. And according to the hot Big Bang model, we can describe quite a number of things in the universe, such as redshift of galaxies, expansion history, the origin of the CMB that I mentioned earlier, we can explain how the first elements of the universe formed, the first few minutes of the universe existence. We can talk about, galactic evolution and distribution, how the large scale structure in the universe, so forth. So on astrophysical scales in particular, it actually does a very good job of describing stellar evolution and black hole formation, black hole evolution, and those kind of things as well. But it suffers quite a lot in terms of the things that we do not know at the moment. And some of those problems I'll mention briefly, and then try to provide some current solutions that are in the literature. So one of them involves early universe problems. For example, earlier I mentioned something about the fact that the observable universe is about 92 billion light years across. So if you look at the distribution of structures in the universe today, there is on large scale similarity in terms of temperature of photons at the very opposite ends of the edge of the universe, not literally speaking, figuratively speaking. And so much similarity in the form of structures. And it begs the question, how did these structures that are so far apart from each other share this kind of information, similar information? So that's called the horizon problem, because of the fact that these things must have been outside of each other's causal horizon at the beginning if they happen to be sharing similar stuff, according to the expansion history, if you do not introduce something called inflation. Things like, why is the universe so fine-tuned and flat? How did the universe form the large-scale structure that we see today if it started off as a smooth structure? And then these less known problems, especially if you're not doing some related to particle physics and so forth, this antimatter-matter problem. Why is there an asymmetry between antimatter and matter when they were supposed to be more or less of the same order? And then why do we not have magnetic monopoles? So there is this prediction in quantum field theory that showed that there must be a large number of magnetic monopoles. The universe started off in that kind of very hot and very dense environment at the beginning. So where are they? So there are these problems in the early universe problems. And then there is, of course, the issue of this observed phenomenon of the rotation curve of galaxies. The theoretical prediction says that, the farther away you are from the center of the galaxy, the rotational velocity should go like this curve here. But the observations show that as you move away from the center, you actually see the rotation curve of galaxies flattening out. And there is no theoretical prediction of this. And it's only a phenomenological observation. As a result, people start to introduce the idea of dark matter. There must be some form of dark matter sitting in the center of galaxies that does this kind of thing. How about the cosmic acceleration? It was not predicted from theory. It was observed, and people had to scramble and come up with alternative theories. So that's also one of the failures of the standard cosmology. Recently, there is also this issue of so-called cosmological tensions. I mentioned earlier that the value of H naught measured by different groups nowadays is showing consistent variations. If you look at these so-called early universe measurements, like the cosmic microwave background predicted measurements, you get some value that's around 67. And if you look at these other so-called late time local measurements of supernovae and parallax measurements, so Cepheids and stuff, then you see H naught lingering around 73. So there is this mismatch between the values of H naught that one gets. And this is referred to as the H naught tension. And so far, there has been no satisfactory explanation why when we measure H naught using local measurements, we get around 73. And when we measure H naught using early universe measurements, we get around 67. So this is becoming a big issue referred to as H naught tension. Another discrepancy involves, the difference in the measurements of the matter power spectrum that you get from large scale structure data, and that's also becoming a big problem. And the problem now is you introduce a theory that makes this one kind of go away or become less tense, and then you make this one worse. If you make this one a bit better, release the tension here, this one becomes worse. So there's some kind of back and forth in terms of the attempts. Another tension, but not so famous as the H naught and sigma 8 tension, is called the omega k tension, the flatness of the universe. Is it absolute? Is it exactly zero or slightly different from zero? So according to the lambda CDM model, the universe model that assumes lambda as the dark energy candidate and the cold dark matter form of matter, omega k should be zero, but recent measurements show that omega k is not exactly zero. There's some deviation from flatness out there, and no one exactly knows why this is the case. And all these things added together, we are talking about an ignorance of around 95% of the universe. So we only know at most about 5% of the contents and the structure and all the different nuances of the universe. And the rest of the 95% is in complete ignorance. So because of this, there are several alternatives being proposed. One of them is that inflation I mentioned. If you have a universe that started off with an exponentially expanding state, the very early universe, then even if those photons that I mentioned or small structures that I mentioned at the beginning being within each other's causal horizon could have been thrown out of each other's horizon, and now they are vastly separated, but in the past they were in the same causal environment, and as a result we can explain some of the things that I mentioned in terms of the flatness and the smallness and the magnetism. So there's a whole lot of literature on inflation. There's so many models of inflation, more than 100 of them actually at the moment. And each one of them is trying to solve one problem and introduce another. So there is not a complete consistent theory of inflation at the moment, but the general consensus today is that in order for us to explain some of the things that we observe, there must have been some form of accelerated expansion in the very early years. So it involves all kind of physics that I'm not going to go through, but the main important point here is that it also requires some kind of matter called a scalar field, inflaton field, to be more specific, which has a negative pressure for you to be able to explain that early universe. Other solutions apart from inflation involve things like what if the universe is not on large scale homogeneous and isotropic? So you have inhomogeneous or anisotropic cosmological models that one can consider to explain. The other thing is, of course, to modify or extend the theory of gravity on which the whole thing is based. I mentioned earlier that gravity is very important in the expansion history. So if we want to explain things that are not explained by the current theory, maybe the right place to start is the theory of gravity itself. And in this sense, there are so many modifications out there that you can look up in the literature. The purple ones here that you see are some of the models that myself and students have worked on recent years. But there's just so many possible alternatives that look at in terms of modifications. And the modifications usually come in such a way that either you modify the matter content on the right-hand side or the geometry content on the left-hand side. You might say, okay, what's the difference between writing G alpha beta, for example, plus lambda equals T alpha beta, or G alpha beta equals T alpha beta plus lambda? And this is just a constant, right? The difference is more in the philosophical aspect of this. If you are adding something on this side, which is purely geometry, equals to this side, which is matter plus something, it means that something has the nature of matter. But if you put this quantity on this side, on the left-hand side, rather than on the right-hand side, you're treating this modification in the geometry rather than the matter content. So there's a difference on whether you put the quantity. Mathematically speaking, this may not make a difference, but in physics, it makes a big difference whether quantity that you introduce is on the right or on the left hand side. Based on this, there are so many possible modifications that one can make in terms of such considerations, and I say that you can also take a look at what you introduce in the action. The action is from that quantity from which you derive the field equations. And therefore the terms that appear in the action are different for different applications. Some of the latest considerations that people have made in terms of trying to solve some of the existing problems that I mentioned involve things like, what if the quantities that we consider non-interacting, like we assume radiation does not interact with dark energy, dark matter does not interact with dark energy, baryonic matter does not interact with radiation, and things like that. We assume that all these fluid components of the universe evolve independently. In other words, this equation holds for each energy density out there in the universe. But what if this is not true? This comes because we assume that that energy momentum tensor that I mentioned earlier is conserved. If it's not conserved for a particular fluid, then it means that it takes energy from another fluid or it gives energy to another. There's some kind of non-gravitational energy transfer between the different components. And in that case, if there's a non-zero divergence of the energy momentum tensor, you can actually get independent, dependent evolution equations for the different fluids that interact. For example, if here, I'm just using this as a demonstration. If dark matter interacts with dark energy, the evolution of dark matter and dark energy is not independent, but it has to be in such a way that the sum of all the extra terms appearing on this side should be zero, because we still assume the total energy momentum tensor is divergence free. We assume that individual components do not evolve independently, but the total energy momentum tensor is, but not the individual ones. If that's the case, you see that the interaction terms that we introduce on this side should have the negative sign on the next, if you consider only two fluids. And here, for example, in this demonstration, I have assumed radiation and baryonic matter do not interact, but dark energy and dark matter interact. And using this, people have shown that you can reduce some of the problems, some of the cosmological tensions that I mentioned, assuming this kind of construction. But there's so much unknowns, as you can see, as I tried to show. There's so much potential to explore for the next generation of cosmologists in general to dive into. I'm going to stop here, and I look forward.
Thank you, Prof, for the very nice talk. I think this is the time for question and answer session. So you, Julius, go ahead.
Okay, thank you, Prof, for the presentation. I'm quite intrigued by some of the tensors you showed earlier in your slides, like the stress tensor, the Ricci scalar, and as well the lambda. So these tensors resemble the ones that are used in spherically symmetric stars, which I believe come from Einstein's general relativity, otherwise known as the field equations. So now, can we be tempted to conclusively say that some of the components of the Einstein's equations are not only applicable to large scales, because I believe spherical symmetric stars are quite small in sizes compared to the size of the universe. So, and then I was taught as well that some, if not all, laws of physics break down at larger scales. Like you can't compare the smaller scales and the astronomical scales. Thank you.
Right, yeah. So you're right. The basic equation we start with, even if we're modeling something astrophysical or cosmological, is the Einstein field equations, or its modification in some sense, or its Newtonian limit. So you have this equation there, K like this, and depending on your geometry that I assume, for example, let me just quickly take this geometry that I assume. This geometry assumes that the universe is homogeneous and isotropic, and it expands because of this term. But if you remove that term and you have a flat universe in vacuum environment, for example, you get a Schwarzschild metric. So this model would reduce to a Schwarzschild scenario if the spacetime is flat and non-expanding, because the Schwarzschild geometry is static, right? And in vacuum. So in vacuum means there is no matter to curve the spacetime, so it has to be flat. So depending on the geometry that you assume and the fundamental physics that you introduce to the scale, then you have either cosmological solution or an astrophysical solution. So you are absolutely right in saying that the same parameters that we use for modeling astrophysical systems applies here. Can you remind me what the second question is?
It's just like I was just trying to drive to where I was heading to. So it just, yeah. Thank you. You've answered the question.
Yeah. It's just a matter of scale. Astrophysical or cosmological. Some of the things that we assume on cosmological scales, they are insignificant if you look at things on small scale. And some of the things that you think are important on small scales, like the inhomogeneity or the local isotropy that you see, on the larger scale, they become insignificant. So on scales, different physical, the laws of physics do not change, but the effect of things that you introduce may or may not be seen.
Okay, thank you. Nyquist, you were raising your hand. Has he already answered your question?
Hello, can you hear me?
Yeah, go ahead with your question.
So my first question is, you have raised one question, like the diameter is almost 92 billion light years, if I'm not mistaken.
Yes.
Yeah,
Yes.
so
Yes.
so at the very beginning, I mean, in inflating stage,
Yeah.
the diagram we have, so the space was expanding exponentially at that stage. So does it mean, I mean, the expansion after that stage is not that much like the first one? So does it mean the expansion was happening with the speed which is higher than the speed of light at that stage?
Yeah. Good question. Yes. The short answer is that yes, the universe must have expanded at speed faster than the speed of light, at subluminal speeds, we call it, in order for us to have a universe that's now 92 billion light years away. Otherwise, if the universe expanded at speed, at the same speed as the speed of light, for example, at photon travel speed, then the maximum you could reach for the observable universe would now be 28 billion light years, right? And you might think, oh, but can something travel bigger than the speed of light? And we're not talking about something here. We're talking about a phenomenon like an expansion, and it doesn't have some physical limitation like the speed of light for expansion, because the only thing that prohibits something traveling faster than the speed of light is if that thing transport energy, right? So a photon, for example, or a car or an airplane, when it does travel, there is transfer of energy, and that cannot happen, or the transfer of cause and effect relationship. That should not happen faster than the speed of light. For something like an expansion or information, there is no physical law that prohibits traveling for it faster than the speed of
And I have another question. I mean, Einstein, not, I mean, the first Einstein model, he introduced the cosmological constant, right?
light. Yes.
So, I mean, why did he introduce that cosmological constant? Does it mean he noticed the expansion of the universe was, or what was the reason behind that? Or what is the purpose
Well,
of that cosmological
yeah,
constant?
yeah, sure. As I mentioned earlier, if you have this kind of equation, so suppose system did not exist, and if you break down all these tensorial equations into their respective components, you get something. One of the equations that you get is the Friedman equation, and if you solve the Friedman equation, it shows you that this equation describes an expanding universe. In other words, there is a scale factor A, which depends on T, that increases or decreases. By the way, for him, the important thing was that it was either expanding or contracting, not just expanding. It's an evolving universe. And for that time, a universe that was expanding was not acceptable, because, as I mentioned, all the universe people knew at the time was the Milky Way. What does it mean to have the Milky Way galaxy? Where is it expanding into? So there are such thinking at the time that prohibited the idea of an expanding universe, and that's why he put something on this side, to balance the gravitational and matter component in such a way that the universe remains in static equilibrium. So that was the reason why he introduced the cosmological constant. Does that answer your question?
Yeah, yeah. Can I add more questions? I mean, I have two more questions.
I leave that to Christian.
I think maybe we'll just permit you to ask one more, and then we continue with other, because we have 4 raised hands. Ask
all right.
one other brief question. Yeah.
All right. I will make it quick. So on slide 47, the Einstein field equation, I mean, there is, I mean, we can add some kind of modification on that. So what are we doing while we are adding the extra stuffs? I mean, actually you mentioned it, but I didn't get you
Yeah.
up. So can you go through that, please?
So here I said extra stuff can be on the right-hand side or the left-hand side. If the extra stuff is on the right-hand side, it means we're modifying the matter content, because the right-hand side is on the side of TAB, which is the energy momentum tensor of matter. So it could be something like you are introducing a scalar field, or something like a dark matter, or something like exotic form of matter that we cannot see but has some effect on the matter behavior. But if you're adding the extra stuff on the left-hand side, I was saying that it means you are introducing something that behaves like a geometrical type. So you're modifying the geometry on that. That's what I meant. Depending on where you put that extra stuff, it behaves as the dark matter or dark.
All right.
Okay, thank you. Aman, go on with your question.
Okay, this is my question, and good afternoon, distinguished professors. So my main points or the main questions I'm asking or question is that like for example, you said that competing theories for the Big Bang. So the current competing theory that I've researched is string theory and quantum field theory. Will this trend continue on? And are you saying that the universe will do the big bounce model which you've mentioned earlier? Will that happen in the universe? And what you've described is what is superfluid, an advanced form of superfluid vacuum theory. Superfluid vacuum theory just says the vacuum or space is a vacuum, but what you are describing is the vacuum and the matter elements are all fluid and interacting. And if this is correct or how I understanding, yes or no, and say why. And can this model be used to identify new anomalies and understand them? And these models be used to understand anomalies and understand them? And is it possible to find new cosmological constants and invent new scientific studies or ideas? And how can we use our indigenous cosmology to
Hold on, Aman.
improve our scientific field?
Excuse me. If you want to ask question, I think it would be very necessary to be concise, because if you get into a loop, you just be repeating the loop over and over again, and the person that you are even asking the question may find it difficult getting your exact question. So I don't know if Prof understood some of the questions he asked. But
yeah, let me attempt to answer some of the questions, and maybe you can answer. You can answer again in the form of follow-up question.
Okay, go ahead.
So I think one of the questions, if I remember correctly, was about the alternative theories to the Big Bang theory. And yes, that's true that there are several competing theories out there, like string theory has been mentioned, quantum field theory has been mentioned, theory of quantum gravity are there, and so forth. There is this ekpyrotic model, cyclic cosmological model. There are several models, and some of them predict something nicer than the Big Bang model, and others something else. And the problem is, if you predict something and the prediction comes out wrong or right, that's good, because it's a good theory, it has a predictive power. The main problem comes if the theory does not predict anything. It does not have a predictive power that can be confirmed or not, at least in the scale of current technology and timeline. So as much as string theory is very interesting, very elegant and beautiful in mathematical formulation, for example, many people criticize it because it doesn't have a predictive power. And therefore many people do not consider it as a good theory by definition, because of that requirement of falsifiability. And so far, the only theory that has survived all this long, despite all its challenges, is the Big Bang cosmological model. And you mentioned something about the Big Bounce. I mentioned it as one of the alternative scenarios for the far future universe, but the current observations are showing towards evidence towards the flat universe. And if the universe is indeed flat, then it will expand forever, and you will not have that big bounce or big crunch scenario. So it all depends on whether the current observations are predicting the geometry of the universe to be flat or curved or open. I showed in one of the slides, for example, that there is an inherent tension in the current prediction of the omega k parameter, the flatness, the curvature parameter, and the theory predicted by lambda CDM showing a flat universe. If it is slightly negative, as I showed there, it means that it's an open, slightly open universe and may not necessarily it simply means that the universe will not end in a big crunch. If it's slightly positive, it means there is a positive curvature. It means that it will eventually recollapse from a big crunch. So these were, I think, some of the questions that I remember correctly.
Okay, thank you. I think we have to proceed.
Wait.
Paul?
Just one thing, just to say.
Aman, we will take your next question. Let's take some other hands, people that raised their hand. We'll be able to take that some other time if we have enough time.
No, just something quick. I'm just
Paul,
saying that.
go ahead.
Yeah, just a quick thing. So what you're basically in essence saying that if
Paul, go ahead with your question.
yes, so basically in all or simplified, if we continue with this method or understanding, we'll understand new things and anomalies or unidentified things and make new fields in science. Is that what you're saying?
Yes, all the time. Every time we think we have come to a more or less complete theory, we discover something else. This issue of cosmological tensions was, for example, not something people took seriously 10 years ago. It is only becoming a famous problem in the last few years. And once we think we have resolved this tension, something else will pop up. And as long as we keep digging deeper into the nature of the universe, we'll find something problematic, and we tackle that and move on.
Thank you, Prof. Paul, go ahead.
Thank you, Professor.
Paul? Okay, then if Paul is no longer asking question, we can go on with Inyama.
Afternoon, Prof. Can you get me?
I can hear.
All right. So we discussed that the universe has no center. So I want to understand in what sense that is, because one would think that looking at the beginning of the Big Bang, there's an expansion. So maybe it's expanding outwards. So someone would say that is the center of the universe. Is it that because space and time was being created at that point, and then therefore maybe there is no center in that sense? Or in what sense can we say it has no center? Thank you.
Let's cool. Let's just assume that the universe is a sphere for visualization purposes, right? If you have a sphere, perfect sphere, where is the center of that sphere? And we're talking about the universe as being the surface of that, not the interior. You see, that's the point. You cannot really define the center. The universe started in a Big Bang, yes, but it expanded in all directions, isotropically and homogeneously. So you cannot pinpoint to a specific point that you can say, oh, that must be the center. And we're talking about space-time, and it's not just space and time.
Okay. Thank you.
Thank you very much, Prof.
The next person, we have 7 minutes to wrap up question and answer. So the next person is Brian. Go ahead with your question. Brian.
So, okay. I have one question from the last slide. Okay.
Go ahead.
The last slide, you said?
Yeah, last slide. I want to know the significance of baryon acoustic oscillation in measuring Hubble constant.
Yeah, I mean, there's some kind of probe that one can make a connection between the H and some kind of baryonic horizon scale in the early universe that people measure. I don't know about the full detail of how they use that to measure H naught, okay? But there is some relationship that gives you that radius scale, distance scale, and H naught, which they apparently are able to measure. And because this one is tightly constrained, then you can infer what the value of H naught should be from that relation. But the full detail of that calculation, the observational connections they make between the calculation and the data, I didn't look into that. But there's a lot of stuff in the literature that you are interested, you can look at, that gives you the relationship between R and
Okay.
Okay.
My last,
I
okay,
think,
I'm meeting. Hello.
go ahead.
Yeah, my last question from Professor, I want to know what a method used in measuring Hubble constants in a cosmic microwave background.
Yeah, that's when it comes to observations, because I mostly focus on the theory aspect. I have to be honest with you, I don't know how they do measure those things, but what I know is that when they measure a CMB related physics, they assume the lambda CDM cosmological model. And the lambda CDM cosmological model, there is a relationship between the energy density of all the fluid components there and the Hubble parameter. And they use that to somehow infer the value of H naught. But the full detail of how they do measure it from the data, I also don't.
Okay, thank you.
But
Let's
but
read
the
some.
model dependent kind of scenario.
Okay, thank you. Let's read some questions on the chat. Starting from down here, we have, is the temperature of CMB dropping or it remains constant?
So the CMB is cosmic radiation, okay? And in one of the slides, where is it? Just quickly go there and show you how the energy density of radiation and the temperature and the scale factor and the temperature change, for example. You see from this relationship that the temperature drops as 1 over the scale factor. So the bigger the universe becomes, the cooler it is getting, basically, according to this relation. So the temperature of the CMB is getting smaller as the universe expands by this scale factor. And you would expect this, right? Because as I mentioned earlier, as you go back into the far past, into the Big Bang, it becomes more dense and small in size in terms of the scale factor. And the temperature becomes extremely high.
Okay, we'll take one last question from the chat, and the remaining questions, you can send them to Slack. They'll be attended to by the instructors. Then the last one is on slide 40, parallax measurements of HO is equal to 73.48 plus or minus 1.6 kilometer per second. Does the dark energy split stars in a galaxy?
Sorry, does it what?
Does the dark energy split stars in a galaxy?
Does the dark energy split stars?
Does a dark energy split stars in a galaxy?
I see. Yeah, no. So the effect of dark energy on very small galactic or astrophysical scales is again negligible. Its effect only becomes significant on large scale. So I have never seen a theory where the effect of dark energy is significant in a stellar or galactic environment that it splits the star there. No, it doesn't happen. At least in the standard model that we know, such scenarios are not considered viable because the effect of a localized dark energy in a stellar or astrophysical environment is negligible.
Okay. The last question here, would you please send it to Slack? How does dark energy influence the accelerated expansion of the universe, and what are the current hypotheses to explain its nature? Except if Prof wants to answer it, but otherwise we already, this is already 2 p.m. So I encourage you all to send the question to Slack. Nyquist, we called you earlier to ask your question, but we're already we've run out of time, so you can send your question to Slack. So thank you, Prof. Mary, for the nice lecture, and thank you all for participating actively during these two lectures we had today. Tomorrow will be...
Okay. Thanks, everyone. All the best.
Okay, thank you.
Thanks.
So tomorrow we'll be having observational astronomy, and it will be starting at 11 a.m. watts as usual. So we hope to see you all then. Thank you.